So we'll start now. Okay. So good evening, everyone. For our 30th SOAWAL, for today's webinar, we have invited Dr. Anil Kumar Pundir, who is an Associate Professor, Department of Mathematics, BITS Pilani at KK Birla, Goa campus. Today he is going to speak on optimal control problem, a use of Pontryagin minimum principle. So let me introduce Dr. Anil Kumar Pundir and say a few lines about him to all of you. He completed his MPhil from IIT Roorkee in 2000 and PhD from IIT Bombay in 2006. His research interest includes control theory, ordinary and partial differential equations, integral differential equations, finite element method, virtual element method, etc. He has 21 research publications in journals of international review and 3 ongoing sponsored research projects. One of his research scholars already graduated in 2020, and 3 scholars are still continuing under his guidance. He organized and attended numerous national and international conferences and workshops. He visited the School of Mathematical and Physical Sciences, University of Newcastle, University Drive, Callaghan, NSW 2308, Australia, from May 21st to July 22nd, 2016, under the University Impression Program. Dr. Pundir is a life member of Ramanujan Mathematical Society, Indian Society of Industrial and Applied Mathematics, Indian Association for Computer Science and Discrete Mathematics, American Mathematical Society, and Society for Industrial and Applied Mathematics. So once again, I welcome Dr. Anil. You please start your talk on this, your subject that you've chosen, optimal control problem, a use of Pontryagin minimum principle. And thank you so much for accepting our invitation, Dr. Anil.
Thank you for a nice introduction. First of all, it's my pleasure to be here in front of you talking regarding optimal control problem. Okay, so today in this talk, I'm going to keep my talk very, very basic, but still there will be some points where you require more explanation, but due to time constraints, so I'm not going to into that much detail, but definitely you will get some idea. I hope some of you must be doing work in this direction. Here today in this talk, I'm going to talk about only ordinary differential equation and an application of this Pontryagin principle there. Okay, so let me start. So this is going to be my talk. So I'm just going to follow this in this way. So first, I'm going to have some motivation why we are doing this optimal control. Then we'll have some brief introduction regarding this great person, Leo Pontryagin. Then I will talk about optimal control problem, where we can have unconstrained optimal control problem and constrained optimal control. Then I will talk about Pontryagin minimum principle. At the same time, one can talk about maximum principle also. I will demonstrate with examples, and there I will explain one algorithm which is called backward-forward sweep method. And then I'm going to end with some bibliography. Okay. So before taking this particular example, let us introduce what is control problem very briefly. So I'm not going to write any mathematical symbol for the time being. So a control problem is going to involve a system that is described by state variable, and at each time step, the choice of the value of the control variable applied at time t causes a change in the state variable of the system at time step t plus delta t. Okay, so but at the same time, you may have infinite number of control variable by which you are going to have solution for your state system. So then we want to find out best fit. Best fit in the sense that you are going to have some objective function. So then optimal control problem come into the picture. So briefly, optimal control problem is going to deal with the problem of finding a control law for a given system such that specific optimality criteria is going to be satisfied. Therefore, we can say that optimal control problem is a set of differential equation describing the path of the control variable that minimizes the cost function. Okay, so basically it says that you have objective function, whatever it is, subject to the constraint, and the constraint is going to be appearing in terms of the differential equation or maybe some algebraic equation. Okay, so but here in my case, I am going to take only the differential equation as a constraint. So this is a very brief definite idea for what is a control problem or optimal control problem. Now, when we are talking about this optimal control problem, and when we move to the real life problem, so you know that every physical systems are always restricted by constraint on both control as well as state variable. So here I'm just presenting some real life problem in front of you. So this is related to the rocket problem when it is going to send to the space. So thrust deflection of the rocket engine cannot exceed a certain designated value. So that designated value you can take at most 10 to 15 degree. If it is going to violate that law, so you will not be able to send a rocket to this space. Okay, so there is some control parameter is going to work in that system. Second example, which you can have in your real life, aircraft cannot climb beyond certain altitude, else they will lose lift because of low dynamic pressure. Okay, so you this is you must have realized all these things. The speed of electric motor should not increase beyond a certain limit. Otherwise, what is going to be happen? Otherwise, motor is going to be out of control or it is going to be out of order. Okay, so there is a restriction that the speed cannot increase. Current in a circuit must not increase beyond a limit, else some component may burn out. So this is the effect if it is not going to limit. So now the question come, which you can say the natural question: can these constraints be explicitly handled in the control design itself? So answer is yes. Optimal control framework allows us to do that part. Okay, so we can control. When we do classification, one classification I already said in terms of the constraint and constraint problem, but then again we can classify in terms of the when the constraint is going to be appearing on control parameter itself, that is going to be control constraint problem. When the constraint is going to be appear only state variable, that is going to be state constraint problem. If you have some constraint with respect to both the variable state and control, that is going to be mixed constraint problem. Okay, let us go back and see when this control problem got started. So if you go back in 1700, so you know very famous scientist Newton, Bernoulli, Euler. Euler was the student of Bernoulli, Lagrange. So these are the people who started in that direction. And remember that when they were doing this type of the work, there was no computer available. Okay, but if you come after 200 years later, the major contribution towards optimal control theory goes to Pontryagin, Bellman, and Kalman. So Pontryagin is the Russian mathematician. Okay, so I will talk about little more about Pontryagin. Bellman, that is Richard E. Bellman, so who introduced dynamic programming in 1953. So great contribution towards the dynamic programming problem. Kalman, he was a European. I think he worked on linear system and gave a Kalman condition for optimality. Those who works in control theory must come across to those type of the condition, Kalman condition. So very great contribution to optimal control theory. Okay. So because here we are going to use Pontryagin principle, so let us talk about little bit about the Pontryagin. So as I mentioned, he was a Russian, and his lifespan is September 3rd to September 3rd, 1908 to May 3rd, 1988. He was from Russia, Moscow, Russia. Interesting thing which we as a normal person we cannot think about. He lost his eyesight at the age of 14 years due to some stroke explosion, and still he has contributed so much in mathematics. So despite his blindness, he was able to become one of the greatest mathematicians of the 20th century with the help of his mother, who read mathematical books and papers to him. He entered Moscow State University in 1925. He has significant contribution in topology, especially in 1930s and 1940s, which was translated into several languages. Late in 1940s and 50s, he got very much interested in optimal control. And as a head of Steklow Mathematical Institute, he focused on general theory of singularly perturbed system of ordinary differential equation and maximum principle in optimal control theory. In 1955, he formulated the general time optimal control problem for a fifth order dynamical system describing optimal maneuver of aircraft with bounded control function. And so far that was never done before in a good analytic sense. To invent a new calculation of variation, he spent 3 consecutive sleepless nights and came up with the idea of Hamiltonian formulation for the problem and the adjoint differential equation. So here, when I'm saying a Hamiltonian formulation, I'm talking about with respect to optimal control framework. So he developed that part. Okay, Hamiltonian come picture in very before Pontryagin, but working that idea with optimal control with respect to the optimal control theory, he only presented that. His other contribution include similar perturbation theory and differential game theory. He and his co-workers were awarded by Lenin Prize in 1961, which is very prestigious award in Russia. Okay, so let us come back to the other problem. So first, I'm going to talk about the control unconstrained problem. Objective is to find an admissible time history of control variable ut. You can say that t is going to lie between t0 to tf. So t0 you can say initial time or when the experiment is going to be started, or when you are going to start your reading. Tf is going to be the final time, which causes the system governed by so this is the system which we are talking about. X dash is equal to g txu. So g is a function of t, T you can take as an independent variable, X and U are going to dependent variable. X is state variable, U is going to be control parameter or control variable. So G is going to be a function of T X U to follow an admissible trajectory. So it means that we want to control some trajectory from the initial point to the final time. Okay, so you can take one control program in that sense. And at the same time, we want to minimize or maximize a meaningful performance index, which is represented by this JU is equal to HTF XF. H is a function of TF XF. TF means, as I mentioned, final time, and X is going to be at final time. Plus integral T0 to TF FTXU dt. Forces the system to satisfy proper boundary condition. Okay, I will come to that. What are these boundary condition? If I summarize this particular part, we want to minimize or maximize the cost function or objective function or performance index 1 subject to the constraint x dot t is equal to g txu, subject to the boundary condition x0 is equal to x0, tf is going to be fixed, and tf is going to be free. Okay, one can generate many cases from here. So one can keep free tf also. Okay, tf is going to be free, xtf is free, xtf may be a fixed number or constant. So there are different case one can take. So I'm going to consider this case when x0 is going to be x0, tf is going to be fixed. Fixed means that you have some number that is let us say capital T, or you write itself as a tf, and xtf is going to be free, means that you are going to find out some expression, and then you can find out what is the expression at t is equal to tf. Okay. Now, this is regarding this performance index or cost function. So if the cost function contains the only, so this HTFXF, this is called terminal cost. So if cost function is going to contain only terminal cost, then it is called a measure problem. If it is going to contain only integral term, then this is called Lagrange problem. And if both the terms are available, then this problem is called Bolzano type problem. For our purpose, here I'm not talking about explicitly what is f and g, but according to the requirement, f and g are going to be continuously differentiable function in all the three argument in appropriate space. Okay. Now, if you define argumented cost function as j bar, which is going to be a function of u. Why I'm writing only u? Because if you see state equation, x dot is equal to g t xu. So if you change u, your solution is going to be changed. So your solution is going to depend on u only. Okay. So therefore, I am writing only the objective function with respect to u. Okay. But indirectly, this x and lambda is going to be there. But these are function of u. Okay. So argumented cost function, if you define, is going to be j bar is equal to h plus t0 to tf integral f plus lambda t g minus x dot dt, where lambda is known as adjoint state or co-state vector, or adjoint vector, adjoint state. So if you are handling a vector valued function, then it is going to be vector, otherwise it is going to be a scalar only. Then we can define one Hamiltonian which does not contain any differential term inside the integration. There are two types of the formulation. If you have seen, one is Lagrangian form and other is going to be Hamiltonian. So Hamiltonian is not going to contain any differential term, but Lagrangian you can have this differential term inside this when you are going to define Lagrangian. So this is a slight difference when we are talking about these two formulations. So let us say Hamiltonian function is going to be h, which is a function of t, x, u, and lambda. So t is independent variable, x is a state variable, u is control variable, and lambda is co-state variable. So which is going to be equal to f plus. So this f is going to come from the objective function. So if you see, this was our objective function. So the term which you have inside the integral, that f plus lambda g. So since I am writing as a vector form, so lambda t, lambda transpose g xu. So it should satisfy the matrix product that we are talking about here. Okay. If it is in a scalar only, so lambda transpose is going to be lambda only. So when we have defined this h, then we can talk about first variation. Okay. So let us say this first variation is going to be delta j bar. And since, as we have said, that f and g are going to be continuously differentiable function, so we can, this 6 is going to be well defined. So delta j bar is going to be delta h plus t0 to tf, delta h minus delta lambda transpose x dot minus lambda t delta x transpose. So here we are using this chain rule, okay, multiplication chain rule we are using here. So that's why we have these two extra terms here. Okay. So if you talk about individual term, delta h tf xf is equal to, that is going to be delta xf, except you are talking about derivative at the final time with respect to x. So delta xf represents that part. So del h upon del xf. So only one term you are going to have in this representation. If you see, if you talk about its derivative with respect to xf, so del h upon del xf is going to come here. So that only I have written. Similarly, if you talk about delta capital H, so delta x transpose del h upon del x plus delta u transpose del h upon del u plus delta h transpose del h upon del lambda, because h is going to depend on this variable. Okay, so you can see that how it is coming. Similarly, you can talk about integral 0 t0 to tf lambda t transpose delta x dot dt. X dot means that we are talking about derivative with respect to t. So you are using chain rule, integration by parts. So lambda transpose delta x, which is going that is going to, so you are going to take a boundary minus t0 to tf delta t upon delta t, delta lambda upon delta t transpose delta x dt. So if you see, this term is going to be 0 at t0 delta x0, because contribution, so x0 is a fixed quantity, so variation with respect to x0 is going to be 0. So that's why this condition is going to be 0. But xf is not, so xf is free, so xf is not a fixed quantity, so this contribution with respect to this upper boundary is going to remain there. Okay, so that is going to be the final expression, or this also can be written. Okay, so maybe I will write in the next slide. So when you combine all these expressions and substitute in delta j bar, so you have expression 7. Okay, and you know from fundamental theorem of calculus of variation, we say that the variation of j bar must vanish for an optimal. So if optima is going to be exist, it is going to be exist at critical point. So that only you are talking about. We are saying that optima is going to be exist. So it is going to be exist at critical point. So delta j bar is going to be 0. So basically you are trying to find out its critical point. Okay. So when we do this, so because here we are saying that delta j bar is going to be 0. So delta j bar is going to be 0 when this and this is going to be independent of increment. Or okay, so because of that, this is going to be true if and only if all these terms individually are going to be 0. So for example, del H upon del XF minus delta H is going to be 0. Del H upon del X plus delta lambda dot is going to be 0. Delta H upon del U is going to be 0. Del H minus del H upon delta del lambda minus X dot is going to be 0. So because of to happen this particular information, so all the individual terms are going to be 0 unless it may not be true. Okay. So using that information, we can write X dot is going to be delta H upon del H upon del lambda, which is nothing but G, which is coming from the constraint. So what it says that if you differentiate Hamiltonian with respect to adjoint variable, okay, you will get back your state equation. Similarly, co-state equation, what it says that if you differentiate with respect to state variable, this Hamiltonian, you will get co-state equation. Okay. Then optimal control equation is going to give you del H upon del U is equal to 0. So from here, you are going to calculate control where the optima is going to be exist. Okay. Then we have boundary condition. Lambda F is going to be del H upon del XF. Xt0 is equal to x0. This is given to you. This particular part is going to come from the derivation, which you can see from here. Okay. So this part is going to give you the boundary condition. Okay. For the adjoint variable. Okay. Some remark when we have this system, you can say state and co-state equations are dynamic equations, which is clear that you are talking about dx upon dt, d lambda upon dt, and if one is stable, the other one turns out to be unstable. Optimal control equation is a stationary equation where what was that equation? Del H upon del U is equal to 0. From there, you are getting uh, U expression. So that is going to be one stationary equation. Okay, no change with respect to time. Boundary conditions are split. It leads to 2-point boundary value problem. So if you see here, when we are talking about this state equation, x dot is equal to g t x u. So then you have an initial condition xt0 is equal to x0. So this is first order differential equation. So you require only one condition to solve this equation. But when we talk about this co-state equation, so here you see that co-state equation, the boundary, you can say the condition is coming at the end point, at the last end point. Okay, so lambda f, you are talking about t is equal to tf. So for state equation, it is initial value problem. For co-state, you are having condition at the boundary, second endpoint. Okay, so that's why we are saying that you are getting a 2-point boundary and lambda. But at forward, at the initial co-state, because the so this is known as curse of complexity. Okay, but we can handle such situation. Okay. Traditionally, this 2-point boundary value problem demand computationally intensive iterative numerical procedure, which I am going to explain at one algorithm. Okay, after some time. In this particular example, which I have explained till now, there was there was no constraint with respect to control. So control control parameter was free, you can say. Now here we are going to put constraint on the control parameter. Okay. So if we define this problem, so we want to find an admissible time history of control variable ut. T belongs to T0 to Tf, which causes the system governed by x dot is equal to admissible perform T0 and boundary condition. Okay. But here I'm just going to put one more condition that u is going is going to taking norm because we are handling u as a vector. Okay, if it is going to be a scalar valued function, then it is going to be mod u is less than or equal to some quantity m. Okay, so this extra condition we are going to have. So this is going to be control constraint problem. This we are going to have handle little bit technically, little bit differently, whatever we have done. So when we talk about the u star, okay, local. So ut minus u star is going to be absolute value I'm talking about is going to be less than epsilon. It may in a small neighborhood. Whenever you have this expression or this information, you are talking about a local minima. But if you can find out, uh, or if you are going to find out u star in such a way that for a sufficiently large epsilon, ut minus u star absolute value is going to be less than epsilon, then you are going to have uh, global minima or maxima you are going to talk about. Okay, so this is delta ut, the deviation or variation uh, from the optimal control, which we have represented by delta u. So going to be u is going to be talk about function. So we start delta equal to 0, and if you substitute u in terms of u star and delta u and expand with the Taylor series expansion, you will get delta j u star delta u plus higher order terms. So we are going to neglect those higher order terms. So you are having only delta j upon delta u, delta u. Okay, all these things you are talking about at u star. So when you have bounded control, or norm of u is going to be less than or equal to m, delta u is no longer arbitrary. I have taken calculated individual uh, uh, u star delta del h upon del u is not going to be 0. Okay, so this implies that we cannot take arbitrary variation around the boundary value. Therefore, we cannot take delta h upon del partial derivative we are talking about del h upon del u is equal to 0. So this we cannot take. So this is a difference when we are talking about control constraint problem and a normal control problem. And I'm going to see this boundary. This is so in the interval TA to TB, u star is going to match with u. Okay, but here there is a deviation which is given by u star minus delta u, and similarly you have the deviation here in this region. Okay, so condition delta j is equal to 0 is valid only if u star lies within the boundary for the T0. This time here 0. If you are going beyond TF, only T0 TA 0. Okay, that we are talking about. Let me to explain one example with respect to this part. Okay, so necessary condition you can have for such type of the problem. So delta j is going to be greater than or equal to 0. For u star is going to be optimal solution. and delta U is going to be allowable variation about U star. And if you recall that equation 7, okay, so uh, uh, so the in control constraint problem, variation in core state can be arbitrary, and this gives. So when you talk about derivative with respect to lambda, you will get a state equation that is going to remain same as you have done in the previous case. Similar thing you are going to have with respect to core state equation h upon delta x. Also going to be known with respect to lambda partial derivative of, but with respect to u, that is not going to be 0. So that we have to handle separately. Okay. So if you take uh, deviation in j bar, okay, so that is going to be integral t0 to tf delta h upon del u del h upon del u transpose delta u dt. So this you can write as u is lambda. So there to be derivation which I tx be greater than 0 for a small derivation is going to be where delta u is arbitrary than or equal to 0. That property with respect we say that x is going to be less than or equal to h lambda. For I'm talking about, okay, with respect to that you are talking about x and lambda. Okay, so necessary condition for optimal for constraint optimal control problem is reduced to find a control u star such that this condition is going to be satisfied, or you can say this condition is going to be satisfied. So this is known as Pontryagin minimum principle. Similar thing you can talk about the maximum principle. Only thing is are going to be this symbol is going to be greater than or equal to. Pontryagin, we can say that these are going to be continuously differentiable function in their all the three argument. What are those three argument? X and u. So if these are going to be continuous differentiable function, and also it is talking about the going to be convex for u. Suppose control from the with and am I audible? But I don't know. Hello. Now is it okay? Okay. Let me go. So the solution for all steps. The constant state equation going to have h upon delta lambda. State equation again from the necessary condition of f. We have 2 condition is going to be satisfied. X0 is equal to lambda f is equal to Tf. Derivative of h with respect to condition, then h you constraint and press the control del h upon del u is going to be 0 only for unconstrained control problem. Okay, the problem where I have not taken control parameter as a bounded control. We are talking about that case. These results gives only necessary condition. Okay, for sufficient condition, one has to see condition. Course must and this second positive the minimizer convex function. Let's talk about one simple. You already know points, and so you connect that this sir you already know that. So let us try to optimal control. Fine. Between two is going to be ds and dx rectangular coordinate square and square plus dt. Here you can write it by you have one where x dot t is equal to we want so the length s between two x j. Okay, so let us define our performance index, that is s is equal to j. J is the because we have given in previous slide notion for objective function j. So because of that only I'm writing t0 to tf square root of 1 plus x. Okay, control parameter. So optimal control integral 1 plus ut and subject to the constraint, because I have so that only I have to ut. I'm value and also value some number I have taken. So now we are defining Hamiltonian. This is f. This is our g. From here you will square root of 1 that you are going to get to be not see when you simplify. Okay, one some constant integrate this so that c so that I have taken so x dot plus c2 when you are going well control and with respect to that given u star we are x star. So see you have two boundary there, so you can calculate. So x dash which is going I just gave it one I this to find out as is okay. Okay, so 1/2 already it is. Much time I can take. So maybe I that you see X1 where subject X0 is and time in this case maybe because I have an algorithm. Initial 0 and 3 plus u square is the state equations are given by this initial condition and x4 0 which we are going to D, E, G, A. These are the U is defined 0.9. Okay. Hamiltonian. So the one because there are adjoint variable you are lambda 2 as we mentioned taking derivative we will get in derivative with respect variable you will get at equation with respect to so since objective function endpoint is missing because of that 0 so lambda 3 is equal to 3 is going to be the control whenever hello I just going so because equation is going to adjoint equation is in a backward a method so that method you see quickly make a parameter solve in forward time the equation in back way of the parameter you which I have desired accuracy. So I to solve equation and the first order, fourth order for this system. plot these graphs with the solution. The time concept. My aim was for the control. With this, I am references. This is not my general. I'm working in a control equation. The problems the growth models, testing another explicitly equation model there. So I will restore question, please ask me. To give you just a but those who are them, it may be write in chat box. It seems there the network issue. So actually, I'm that it may be that whether it was
problem is from our audible in our department.
no, you.
Yeah. Too soon. Okay.
Yeah, you. Yeah, your voice.
I think
Professor Manjula, can
sure. Any questions from
no, it seems that this,
thank you so much for this nice and presentation. I think I think everybody so much. So, Abhijit, so I request the department. The problem is there. Problem is there.
Yeah.
Me, yeah, Dr. Abhijit. Thank you that you are participating. Thank our president Manoj Ranjan Naik for his in the field of research. Thank you, thank you, and thank you, everyone. Webinar over here. Thank you.